Okay. Hello, everyone, and thanks for attending today's presentation on exploiting vulnerabilities in Azure Stack Hub. My name is Anna Dubovitskaya, and I'm a software engineer within the Edge and Platform organization at Microsoft. So to start with, we'll cover some background information that you'll need to help make this presentation make sense. And then we'll get our hacker hats on, and I'll lead you through some actual exploits we've had in Azure Stack Hub. Of course, it really wouldn't be such a useful presentation if we didn't actually learn anything. So after that, we'll discuss what you can learn from these vulnerabilities and cover some go-tos that you can take back with you to your own work. And for those of you who are attending the live presentation, we'll also have time for a Q&A at the end. So with that out of the way, let's get started. Azure Stack Hub, for those of you who aren't familiar with the product, is a hybrid cloud solution offering by Microsoft within the Azure Stack product family. It allows customers to have the look and feel of Azure while hosting the actual hardware and data on premises. A common market for products like this are customers who may have had government rules or regulations that prevent certain types of data, like healthcare information, from leaving the boundaries of the country. With a traditional cloud offering, you wouldn't be able to control where that data lives, but with Azure Stack Hub, you can guarantee it. Azure Stack Hub differs from Azure in that a customer owns a particular Azure Stack Hub instance, also called a stamp or environment. Rather than having Microsoft engineers manage the stamp, the customer is expected to have their own engineers who fulfill basic operational tasks or perform routine maintenance. For this presentation, those are the people we care about, as they're the ones who actually interact with the Azure Stack Hub stamp, and you will hear me refer to them as Azure Stack Hub operators or cloud admins after the built-in credential used for this purpose. Most importantly, Azure Stack Hub is sold as an appliance. In other words, unlike Microsoft engineers in Azure who have full insight into the inner workings of Azure, an Azure Stack Hub operator has no insight or access into the internal workings of Azure Stack Hub. They simply host the appliance. What they can do in Azure Stack Hub is severely locked down, limited to only very, very basic tasks like applying updates, keying off certificate rotation, collecting logs, so on and so forth. Anything more than this requires the Azure Stack Hub customer or operator to reach out to Microsoft to open a support case. One of the ways that an operator can interact with our Azure Stack Hub stamp is through something called the privileged endpoint, or the PEP. Interaction with the PEP is completely PowerShell based, and operators will typically have something called a jump box, where they can spin up a PowerShell window and access the PEP with their cloud admin credential. Now, there are usually two flavors to the privileged endpoint. The locked PEP is usually what we mean when we talk about the PEP. It's what's accessible to the Azure Stack Hub operator by default, and it is super low privilege. You can only run a very limited set of predefined or whitelisted commands, such as diagnostic log collection or certificate rotation, and you can't even autocomplete any commands. However, when things go wrong, the PEP is also the primary way for Microsoft engineers to get access to the stamp for troubleshooting purposes. Since it's a bit difficult to do anything when the stamp is so locked down, once a support case is raised, a Microsoft support engineer can do something called unlocking the PEP session. This process is also called breaking glass, and what it does is it elevates the PEP session to domain admin level privileges and basically gives you free reign on the Azure Stack Hub infrastructure, with the caveat that there's a support engineer on call with you monitoring your every move. Now, if I look at these two flavors of PEP through the eyes of an attacker or some malicious user, one of these stands out pretty clearly to me. And since I probably don't have the best of intentions, it would be even better if we had no Microsoft involvement at all, since I can't really do anything naughty if I have a support engineer breathing down my neck and watching my every move. But since Microsoft is the one who unlocks the PEP for me, in order for my dreams to come true, I would have to be able to break glass and elevate the locked PEP session myself. So is that possible? Obviously not intentionally, right? But perhaps there's some vulnerabilities that can be exploited to make it happen. So let's find out. In this next part, we will assume the identity of Mr. Hacky McHackerton, an Azure Stack Hub operator gone rogue. Well, actually, a bit of a side note first. The following exploitations are all variations of elevation of privilege. To simplify things, I'm going to assume that we've already obtained the low privilege cloud admin credential. At the end, I'll discuss why that's not actually a big deal and pretty easy to do. But in the meantime, let's just roll with it. Okay. So now we can put on our metaphorical hacker hats and get started. So to understand what we will need to do and fill out the rest of these steps, first we need to learn exactly how the PEP Unlock process works in Azure Stack Hub. So here's what it looks like. And I know some people are probably going, wait a minute, Mr. Hacky McHackerton, like how do you know that this is what it looks like? Internals are internal. Well, there's extensive public documentation detailing the process online, including what unlocking the PEP gives me, which is full admin capabilities and full reachability into the infrastructure, which is exactly what I want. The commands that I need to run, that the PEP process runs on 3 virtual machines called ERCS, and how, as well as with what, the unlock token itself is generated. Oh, and worst case, we also have a patent for this online. Go Microsoft. So to condense all of that, this is what the PEP Unlock process looks like. You basically, as a cloud admin, you open a support ticket and you contact CSS and you log into your locked PEP, which is what everybody has access to. And you run a command called get support session token. That will generate a request token using the public key of the PEP certificate that is on the stamp itself. That will give you a request token for breaking glass. You then pass the token on to CSS, who will log into their own support website, which holds the private key of that corresponding PEP certificate, passes in the request token, and gets a response token back. They then pass this on to the cloud admin, who can run the second command, unlock support session, and pass in that response token. Once that's verified, the PEP is unlocked. So at this point, let's head on over to an actual Azure Stack Hub stamp and demo what that first process would look like. Again, I'm simply following the public documentation here, logging on with my cloud admin credential. And now that I'm in, here's what the break class request token looks like. And since I don't have the corresponding private key for the certificate that was used for the token, at this point, I would need to give a Microsoft support engineer that request token so that they can generate the matching response token using their private key and elevate my PEP session for me. However, that doesn't make Mr. Hacky McHackerton very happy. I don't want to talk to Microsoft, right? In fact, what I want to do is shift the process outlined in red to something that looks a little bit more like this. That way, we don't need Microsoft to generate the response token for us, which means that we'll be free to gallivant about with our newfound domain admin privileges without some support engineer on call watching us. For that to work, we will need to create our own certificate so that we, not Microsoft, can generate the response token with its private key. But we will also need a way to get that public key version of that certificate onto the ERCS virtual machines where the PEP sessions are hosted. And that might prove to be a little bit harder. So to summarize, we just got an understanding of the PEP Unlock process, and now we know that the next steps will be our very own PEP Unlock certificate and a way to get that certificate onto Azure Stack Hub. Okay, so how do we do that? How do we accomplish the second and third steps? Well, first, we need to gather some information so we know exactly which certificate we want to create and how. Now, if we take a closer look at that response token generated in the locked PEP session, there's something that immediately stands out to me. And it's these 5 characters right here. Why? Well, if you've been around certificates long enough, you've probably noticed that most base 64 string representations of X5 and 9 certificates start with MI or MII. There's an actual reason that that's the case, but I'll leave those details as an exercise to the viewer. Anyway, that little fact means that this part right here is most likely the start of a certificate. And if we look back at the public documentation describing the request token contents, the MII part likely corresponds to the start of the self-signed certificate. However, what about the 5 characters right before it? It could be the randomly generated session ID or the timestamp, but if I try requesting a support session token multiple times, that value stays the same, which doesn't really match the behavior I'd expect from a timestamp or something that's randomly generated. To help me get a little bit further on this, I'm going to collect Azure Stack Hub logs for the stamp, which is another functionality available to me from the locked PEP session, and see if I can find this particular substring somewhere in there. And it turns out that those 5 characters are actually part of a thumbprint for what seems like the PEP certificate. I mean, the subject name says privileged endpoint access, so it's kind of a safe bet. And just these 2 logs alone give us all sorts of nice, juicy information, like the exact certificate subject name, what machines it lives on, what certificate store it lives on those machines. And now that we have that, let's generate our very own PEP Unlock certificate and stage it on our jump box. So here's my certificate generation code. I have the certificate subject name matching the PEP certificate from the logs. And I'm using my very own, definitely not Microsoft CA as the root, as well as some generic signing certificate flags. Hit run and copy the output certificate files onto my stamp. And so here is the public key version of my fake PEP certificate, and the other 2 are the public key version of the root and the PFX file containing the private key of my fake PEP certificate, which we'll use to generate the response token later on. And with that, we've successfully completed our second task. So now what? We have the certificate, including its public key, private key, and the root certificate that signed it, but it's not in the Azure Stack Hub stamp just yet. Remember, we need the public key version of our fake PEP certificate to be on the ERCS machine so that the break glass request token is generated with our certificate, one that we can generate a matching response token for. To get a clue for how to do this, let's go back to the logs we gathered earlier. Specifically, this log right here, where I can see details about my external certificates. For those of you who may not be as familiar with Azure Stack Hub, there is a set of about a dozen certificates that the customer is expected to provide during initial deployment. We call these external certificates. You can then rotate these certificates whenever you want with yet another well-documented PEP command. To do that, you have to provide a new set of about a dozen certificates in the form of PFX files that contain the leaf as well as the chain of trust. So in our stamp, for example, the PFX contents would look something like this. We have 1 leaf certificate, 2 intermediate certificates, and a root certificate. And only the leaf certificate has a private key. The rest are public key certificates that are used to establish trust, which is why these are often called the chain of trust certificates. Now, traditionally, root certificates get placed in the machine's root certificate store, intermediate certificates in the intermediate store, and leaf certificates with private keys in the my store. This helps the machine trust that certificate and the certificate authorities that issued it. However, the logs show that all of the certificates I provide, even the chain of trust ones without a private key, are ending up in the my store on all machines, including the ERCS machine, which is just where we want our fake PEP certificate to live. In other words, we can take advantage of external secret rotation to help us get our fake PEP certificates onto Azure Stack Hub. The best part is I don't actually need to go get new certificates for this. I can just reuse the same PFX files from the initial deployment of Azure Stack Hub or my last secret rotation. To do that, I just simply take the original PFX files, unpackage them, and then just repackage them to include the fake PEP certificate that I had generated. So now the PFX file would look like this.
Hey, Anna, do you mind just zooming in when you have this? There's we have a request from the audience that text looks a little bit small, so maybe you could use the zoom in tool from the PowerPoint to zoom in on the.
I can try.
Thank you.
Not sure if that's yeah. Okay, yeah. Let me know if it gets too bad. Okay, so let's go back to Stamp and see this in action. Here's what one of the original PFX contents looks like. We have the leaf certificate matching one of our dozen or so endpoints, and 3 public key certificates corresponding to the chain of trust. I will then repackage these PFXs to include our fake PEP and its chain of trust. And as you can see now, the new PFX has 1 leaf and 5 public key certificates. With that done, I can now kick off external secret rotation. Again, just following the documentation here. Restarted. I'll just let it play through. Yep. So there we have the 5 certificates again. And now we can kick off secret rotation with the same command that we saw in that public documentation earlier. And so external secret rotation takes somewhere around 30 minutes. So 30 minutes later, it's done. And what I'll do now is I will go and I will generate myself a new unlock request token. Hopefully that wasn't too bad. And if you were paying close enough attention or you were able to zoom in adequately enough, you might have noticed that the request token now has a different 5-character prefix, which matches our fake PEP certificate thumbprint that we had, which makes us pretty happy because it means that we've successfully tricked the stamp into using our fake PEP certificate instead of the legitimate Microsoft one. And so with that, we've completed the last thing we needed to do, and we can finish breaking glass ourselves. Now, to save us some time, I have already pre-created the response token generation script. There's actually nothing particularly difficult about figuring out how it works because we have most of the details in our public documentation. And worst case, there's actually no limit on retries. So even if I didn't quite know the exact response token format, I could just try variations until it works. So first things first, I will copy over this request token and take it to another window where I have my handy dandy response generation script ready and pass in the token that I copied. As well as the location of the fake PEP certificate private key from the PFX. In return, I get this response token, which I will also copy. And back in the original window, I need to run that second command, unlock support session, and pass in that token that I had. And voila, I have successfully broken glass and can now run whatever commands I want. So let's step a little bit behind the scenes and look into the actual Azure Stack Hub internals and learn about why that worked. So the normal request token generation process in Azure Stack Hub looks a little like this. We get the latest certificate on ERCS VM with the privileged endpoint access subject name. We see if the certificate chain builds. And if that's good, then does the root of the chain match the hard-coded root thumbprint? And if yes, we generate the token. If at any point we fail any of these, we fail everything. It turns out that at one point we had a feature to allow certain customers to bring their own PEP certificate. And our implementation of this feature accidentally allowed anyone to bring their own PEP certificate. The key to this is a bug in the thumbprint validation code for the request token, where we simply return true for any root certificate that doesn't match the hard-coded thumbprint of the official Azure Stack PEP certificate root, because we're just assuming that it's the side-loaded certificate. And that's exactly the path that our fake PEP certificate took, allowing us to generate an unlock request token using a certificate that we control instead of Microsoft. But if I put my hacker hat back on, while it's pretty cool to have an unlocked PEP session in my control, it's also a little bit annoying. I have to go through the break glass process each and every time I want elevated privileges. Plus, each session only gives me a maximum of 8 hours to work with. It would be great if there was a way to just log into the PEP session directly, but if I tried to do this on the stamp with my cloud admin credentials, I would just get an access denied. And that's just not fun. In fact, if I were Mr. Hacky McHackerton, I'd probably argue that this is an incredibly egregious bug that needs to be fixed immediately. So how do bug fixes get shipped in products like Azure Stack Hub? Much like most products today, Azure Stack Hub has updates and hotfixes that operators can download and apply to their stamps. However, it's extremely unlikely that Azure Stack Hub would ever release an update that magically elevates me to a domain admin, but maybe we could just make our own. To do this, we want to ideally piggyback on already existing hotfix or update package infrastructure. That way, we don't have to worry about trying to figure out how updates work in Azure Stack Hub or the details of making one ourselves, although this is pretty accessible information. In my Mr. Hacky McHackerton mind, that process would look a little something like this. Just download the Azure Stack Hub update package, add a step in there to make myself a domain admin, upload this update package back to the portal, and kick off the update. First, let's download one of these update packages and see what's inside. I've chosen a hotfix package instead of a regular update package just because they're shorter to run, but they're essentially the same. And if I scroll to the bottom, I can see that there are two files to download for this hotfix, a zip file and a hotfix XML file. According to the public documentation, one of these is the actual payload zip file, and the other is something called a metadata XML file containing information like the file hash and other details corresponding to the corresponding update package. So let's finish downloading those two files and copy them over to some staging location on the stamp. And after I do that, I also want to confirm that the file hash is the same. So get the file hash of the zip and compare that value to the one that we have in our metadata XML file. And as you can see, the two match. Now, unfortunately for us, much like the documentation also states, the metadata XML does appear to be signed by a certificate that is trusted by the Azure Stack Hub system. Now, this may seem like a problem to us at first, but because if I add a step to make myself a domain admin, the file hash of the update package will change, and the signature will then become invalid. However, all this means is that I will simply need to add a new step to our list to update the file hash and re-sign the metadata XML with a certificate that is trusted by the Azure Stack Hub system. And if you were paying attention during the last exploit, you already know that Azure Stack Hub has a handy-dandy way of getting whatever chain of trust I want onto every single infrastructure VM with external certificate rotation if it wasn't already there by default. So now that we've got that part figured out, just like last time, we can begin the process of gathering the information we need by getting more logs, this time the Azure Stack Hub update logs, using yet another whitelisted command available to me from a locked PEP session. Now, these update logs can get pretty verbose, as in nearly 500,000 lines verbose. But if I just try doing a simple string search for the obvious domain admins, which is the official security group name in Windows for domain admins, the very first hit takes me to the exact information I'm looking for, which is what accounts get added to this group, and in what step of the update process this happens in. And if I scroll down a bit further, I can find the section that pertains to the cloud admin user, which is our low privileged user that we're starting with, which is also me. So that was pretty easy. Even better, because a good majority of Azure Stack Hub code is written in PowerShell, which doesn't compile to anything, I can pretty quickly find the corresponding code just by simply searching the contents of an update package for the logging statements that I see in the logs. Now, it would be great if I could just insert make me a domain admin into that PowerShell file. But remember, the PowerShell files in the update package are signed. And so changing or adding to the PowerShell code would render this signature invalid, and our code would be blocked from executing by code integrity, which is a Windows feature that prevents malicious or untrusted scripts from running on Windows machines. So I'm going to need a new plan. Luckily for me, the code itself seems to be just a bunch of for each loops that iterate over a list of objects pulled from a different source. And once again, with a bit of basic pattern recognition and clever use of the search function on my text editor of choice, it turns out that the source for these values comes from an XML file called customer config template. But what's more interesting is that if I go back to my stamp and unzip that update package and find that particular XML, if I scroll down to the bottom of that file, there's no signature there. In fact, other than the metadata XML that the update package comes with, none of the XML files in Azure Stack Hub are signed, mainly because code integrity is primarily concerned with malicious executables, and XML is just, well, XML. So what's in those unsigned XMLs? Well, we have things like detailed account definitions and role XMLs, user memberships, including those of high privileged groups like domain admins, and various action plan definitions, which are things that dictate the set of steps that are run for various Azure Stack Hub operations, such as hotfixes, updates, and secret rotation. So while technically the update code files themselves are signed, adding a step to make myself a domain admin is as easy as adding an extra XML tag with the words domain admins under the cloud admin entry. With that done, I need to repackage the files back up and place them in their appropriate locations. Now, unfortunately, this particular hotfix doesn't include the domain live update step where the magic membership changes happen by default. But again, since those steps are just unsigned XML files, I could just add that in and give it a nice little name while I'm at it. For example, make us a domain admin, the securest of all steps. Plus, doing this will actually make the step easier to spot once we kick off the update. Once that last part is done, I'll zip up the files and create the new and improved hotfix package. And with that, I've completed the second step. To re-sign the metadata XML, I first need to get the new and improved file hash from our new and improved hotfix package to replace the old value in the metadata XML file and re-sign the metadata XML. To do this, I'm using .NET's built-in XML class and that same root certificate that we generated our previous Azure Stack Hub external certificate. Once it says done, I can check out the metadata XML again. And it looks like we got our new signature. Now, it doesn't really look very pretty, but beauty is in the eye of the beholder, so it works. And after getting that third step out of the way, all that's left is to just follow public documentation for uploading the update package to the portal and kicking off the update itself. While I do that, I want to point out that the reason we had to re-sign the metadata XML file, but none of the other XMLs. While Code Integrity doesn't particularly care about XMLs, the update resource provider in Azure Stack Hub does its own separate validation of the metadata XML as part of the update package inspection and validation. And that's where the signature validation that we're trying to exploit comes in. Which we know that we're able to do successfully because the modified update package now shows up in the portal. If it was invalid, it would never be there. So let's kick off the update and wait. And around 15 minutes later, we're hitting the custom step that we added, make us a domain admin, the securest of all steps. And 15 more minutes later, that step is done. And with that, our little bug from earlier has been successfully hotfixed. And I can happily log into the PEP session directly as a cloud admin. No PEP or break glass needed. To prove it, I can run who am I, which shows that I am indeed the cloud admin user, and who am I groups, which shows the cloud admin with domain admin membership. And for anybody who's doubting this out there, yes, the code integrity policy is still on. Much like the previous exploit, the reason that this worked is simply because the update package verification process only checks for a valid chain certificate trusted by Azure Stack Hub, which happens to include customer provided certificates. Without that tiny little detail, I could have modified unsigned XMLs all day long, but my final repackaged update would have never been accepted and happily installed by Azure Stack Hub because the verification process would have failed. With that, let's say goodbye to Mr. Hacky McHackerton for good and see what key takeaways we can get from our experience that could have prevented these exploits from happening. First, a lot of decisions can seem like they don't matter until they do. Let's take the fake PEP certificate exploit, for example. A lot of individual mistakes and missteps came together here to make that exploit possible. We decided to pull certificates from machine certificate stores instead of strings or files because why does it matter where we get the certificates from? We decided to use the My Certificate store instead of the CA root for chain of trust certificates because it doesn't matter what store we use, but it's easier to pull from one instead of multiple, so why not? We decided to propagate certificates everywhere instead of only on those VMs that needed it because it doesn't matter, they're just public key certificates. Nothing sensitive there, right? And finally, we introduced the PEP changes that happened to have a bug. Had any single one of these blocks not been there, and the exploit would have never been possible. But only one of these was an actual accidental bug. The rest were all issues brought to people's attentions who then made a conscious decision not to fix them because it doesn't really matter. And there were always other higher priority things to do and bugs to fix. But the security bill comes due eventually. You only get to choose to pay now or later. Less is more secure. This means less leaving of certificates in certificate stores where they don't belong, and only putting them on machines where they're actually needed rather than, well, everywhere. The less is more secure principle is also at the core of how we fix the metadata XML signature exploit. Instead of any trusted certificate chain being valid, we restricted the chaining validation to only accept those that chain to a Microsoft root certificate. Because obtaining the private key of a valid Microsoft chain signing certificate is exponentially more difficult than just generating my own with a few lines of PowerShell. It's important to note that less is more secure does not mean security by obscurity. It might be tempting to think this way, especially when I keep mentioning our extensive public documentation so many times in this presentation. But obscuring information doesn't make the core vulnerability go away. You are at most simply buying yourself some time. However, if you're going to be so explicit about your internal workings, you better make sure everything works the way that you expect it to. This is where good defense in depth comes in, which is our final lesson. The principle of defense in depth relies on every single component being secure individually. Working with other software engineers, I've heard each of these excuses, and some of them rather often, like, what's wrong with leaving a few certificates around? They don't have private keys. It's not a big deal if, the cloud admin password is leaked. It's not like they can do much on PEP. It's super locked down, super low privileged. All of our files are signed, well, except for the XMLs, but it's just not that important. And while these may be perfectly valid statements on their own, they add up and they add up fast. It's the equivalent of having a lock on every single door of your house and storing your valuables only in the deepest, darkest area of your closet. If you then place a jar with all the keys in your garage, suddenly it doesn't matter how many locks you have. Your defense in depth has been reduced to a single sheet of metal in the form of a garage door. Likewise, I'm sure many of you have had experiences with screen sharing sessions where the other person has had various passwords up on screen in a text file or a sticky note or something like that. We've had incidents where logs had to be scrubbed of credentials that were copy-pasted from troubleshooting sessions. But can you really blame these people? It's like getting mad at your friend for leaving your garage door open a crack when every day for the past year you've done nothing but brag about how many locks you have and how secure everything is. Every time we highlight all of the cool security advancements and measurements we've taken for this or that product, we risk people getting too comfortable with the security components outside of our control, like customer provided passwords. So we need to be absolutely sure that those components can never be a weak link in our security posture, capable of crashing down all of the defense in depth measures we've taken. Because let's be honest with ourselves here, if the only thing that's standing between an attacker and elevated privileges is a single low privilege credential, we've kind of already lost. And if after all that you still don't get why good defense in depth is so important, consider this. Microsoft treats the private key of its PEP certificates as important company property, and any leaks would be a big deal, like all capital letters, at least 3 lures, big deal, right? But the vulnerabilities we saw today mean that we don't even have to wait for somebody to hack Microsoft and leak a PEP certificate. We can just, generate our own. In closing, I think one of the most important things to emphasize is just how easy it is to identify and prevent the types of vulnerabilities covered in this presentation. Everything we've exploited today was discovered and proven by me, and while my mother swears otherwise, there's really nothing special about me. I don't have any kind of formal security training, and I'm certainly not part of any red team or cool hacker organization. And let's be honest, these vulnerabilities aren't some fancy side channel attacks. They're all the product of simple bugs or errors in judgment, yet the consequences are just as significant, allowing me to go from a low privileged account to a domain admin with full internal access to a supposedly locked down product. On the bright side, this means that there are equally easy and actionable things that all of us can do to help fix or prevent these in our own areas of ownership. The first is reframe your mentality. A lot of people I work with talk about attacks and exploits as things that happen to them rather than things that could be actively prevented or stopped. And yeah, there are some really cool vulnerabilities out there that absolutely no one saw coming and may not have been possible to predict. But I'd be willing to bet an equal, if not larger amount of those are just the same type of bad decisions or dumb bugs that we saw in this presentation. So if you're a software engineer, go take a look at your code or your team's code or some other team's code, whatever, it doesn't really matter. And anytime something doesn't seem right, like a bunch of to-dos and security critical code, just take a moment and think about it. See if you can find a way to exploit it and what you can do to prevent it. Double check yourself every time you think the words, "it doesn't matter." Likewise, foster this culture with the people that you work with. Everyone should feel empowered to call out questionable things they see, because just one tiny detail can easily lead to the exploitation of an entire product. And if, or really when, things go wrong anyway, consider making presentations like this one. When we admit our mistakes and share our learnings, others can learn and grow from them as well, and that makes all of us just that much stronger. And finally, the next time you're writing code or public documentation or thinking about how to phrase customer messaging, bring out your own inner Mr. Hacky McHackerton and think of ways that could be exploited by someone who may not have the best of intentions. Because it's always better for you to catch vulnerabilities before someone else does. And doubly so if you can actually avoid introducing these into your products to begin with. Because remember, only you can prevent security vulnerabilities. Thank you, everyone, and I hope that you've enjoyed this presentation.
Thank you, Anna, for being our guest today and for sharing this excellent session with our public community. As well as wanted to thank Alex Napari for helping out here with incoming questions. So I want to give another minute or two to the audience there if they have any questions to raise them in our live event Q&A. And while they're doing that, I will go ahead and just quickly mention some reminders. So basically, the best way to ensure that you don't miss any future webinars or major announcements, please visit our landing page at aka.ms/securitycommunity. This is also where you'll find our webinar registration link and many other links related to the learning content relevant to our security products and their communities. I suggest a good start would be just simply by browsing over the bite-sized product videos that we have, all the Ninja trainings and recordings of the past webinars as well, and each of the GitHub communities for the products. And also, we'd love to hear your feedback on how we can improve on these webinars. And please take a minute by submitting your feedback at aka.ms/security webinar feedback. So going back here to our live Q&A, I see no more questions coming in. So thanks again, Anna. Appreciate it. And I want also to thank all of our community for being part of us and for joining us on these webinars. We hope to see you next time. Goodbye.